Okay, try not to make too much noise. All right, we're gonna start at 3:30. So I'll just open the stream. We'll wait for everybody to join in. Can see this better, hopefully. It's not easy. Mhm. We're gonna start at 3:30. So right now it's 3 and 2 minutes. Okay. So I'm muting my mic so I don't have to send you everything that's going on in my house. And I'll join in back at 3:30. Okay, folks, so let's talk about the new stuff we have. Today's lecture is about correlation. You will find this lecture on the Blackboard. I have it labeled as number 11, and there's a little longer title that talks about the whole content of the lecture, which is about paired data and the Pearson correlation coefficient. There are a couple of things about correlation. So there is another lecture after that, and we're going to talk about it on today is what, Monday, Wednesday, I guess we have class on Wednesday, so we're going to talk about that. But what we're going to be talking about on Wednesday is not going to be on the test. We're going to have the next Monday. So today lecture would complete the stuff we have for the test. And so when it's over today, then this is basically what's going to be on the test number 2. Okay, so what is a correlation? All right. So what I have here is the table and the graph which you have in the lecture. So I made it here on the whiteboard, but you have it in the lecture, so it's nicer there than what I did here by hand. Is that I have two groups of data, or should I say two samples. The first sample is about the group of students, 10 of them, that were taking the calculus quiz. So the first student scored 17, the second 15, the third one nothing, the fourth one 10 points, then the next one 15 points, and so on. So they were scoring anywhere between 0 and 20. And so you have one student here scoring 20, one student scoring 0, and all of the rest anywhere in between. Okay, now you have the same group of students taking quiz number 2, and that's the Y data. So that's a second sample. In this, you have the first student score 15, the second 20, the third one 3, and on you go again. The quiz was between 0 and 20. So you can see the same student scoring 17 on the first quiz, that's an X, and 15 on the second quiz, that's a Y. And then the same student number 5 scoring 15 on the first quiz, 15 on the second quiz. And the same student number 8 scoring 15 on the first quiz and 17 on the second quiz. Down there on the bottom, I wrote the sums of all of the numbers in the X sample and sums of all of the numbers in the Y sample. Now, we call this paired data. Again, because they're naturally paired. You have the same students taking quiz number 1, quiz number 2. So that student, you have a X score, the quiz number 1 score, and a Y score, the quiz number 2 score. So the data is paired. So you have every particular X is paired with a particular Y, because it's referring to the same student. Now, I'm sure you study the coordinate system in the high school or elementary school, and you know that when you have an X and Y, you can actually make a point in the plane, which is going to have an X coordinate and Y coordinate. So I have done that. So you have here a plane in which I have 10 points, and every point refers to a student. So you have, for example, student number 4, first quiz score 10, the second quiz score 15. So you have this student right here. This is actually a point, right? But represents the students. So 10 on the first quiz, X, Y on the second quiz, 15. And you can do it for all of the students. So you have all of the students like that. Every student represented by a point there in the plane. What you should notice immediately that there is some sort of a shape there. It's not randomized. I mean, it's not like you have a point scattered just anywhere. By the way, this is called scattered diagram. Or scattered diagram. Or scattered plot. Or scatter graph, if you like. your calculator can do that. So if you put this in the one list of your calculator, this in another list of your calculator, you can take an option there to make the scatter diagram. But you can make it yourself too. It's not that hard, depending how much data you have. So in this diagram or this plot, you can see that there is some particular shape. The points are not at random. That shape looks like in a shape of some cigar. It goes from left down corner to the upper right corner, which actually indicates something. So there is what we call a trend here. Okay, as you make X bigger, the Y gets bigger. And that is not really a surprise. So when the student scores more on the first quiz, when X is bigger, that student scores more on the second quiz. The Y gets bigger. So as X gets bigger, the Y gets bigger. If you go this way, then as X gets smaller, the Y gets smaller, which means that there is a relation between X and Y. And that is what we call a correlation. There is some sort of a correlation here. Okay, now that's visual. So I can see something like that. I can see there is a correlation here. But now the question is, what do you do with that? Okay, you can say there is a trend here, and that's pretty much it, right? But we are studying science. So in the science, we are doing analysis, we are doing calculation. And so here we can do something like that. Is it enough to claim that we have a correlation? Could we compare that with some other data that we have similar trend? And what would that mean, actually? So Karl Pearson, which is probably the greatest statistician that ever lived and the father of modern statistics, come up with an idea that would quantify this. So it would give you an idea what amount of correlation you have. So you need to assign a number to it. What number would you assign to that? Okay, so his idea is to use something that we now call a Pearson coefficient of correlation. It's actually, the full name for that would be Pearson product moment coefficient of correlation, actually even longer, Pearson product moment linear correlation coefficient. Now that's a really long name. So we're just simply going to call it correlation coefficient. And we're going to refer to that as a Pearson correlation coefficient because there are some other correlation coefficients, some other ideas how to quantify this correlation, is this trend very pronounced or is it less pronounced and so on. Now it will be more pronounced if it's more like a line, it will be less pronounced if it's more scattered and so on. So he came up with this idea. Now, his calculation gave us the first formula we have to quantify this. And that formula is what we call a product of moments. It's actually, so we will use the symbol R, the label R, for correlation coefficient. And basically what he's done is you make the product of the Z value. So you have the X values here in this sample. You have the average. The average would be 11.5, right? The total sum, the total of all of those scores of the students in the first quiz is 115. There are 10 of them, so it's 11.5 on average. And so this is the mean of the X scores, and the mean of the Y scores, you can calculate the same way, would be 13.3. Because again, the sum of all the scores is 133. There are 10 students, so the average second quiz score is 13.3. So since you have that, you have the mean. You can also calculate the population standard deviation. I know this is not a population, it is sample, but you can calculate as if you have a population. So you can calculate population standard deviation, you can calculate population standard deviation of this sample, and then you can get z-values. And I know you studied that in 103, statistics 1. You study how to get the z-values. So if you get all of those z-values, you just make a product. So you have a z for the x value, like x value 15, you can get the z-value of that. You can get the z-value of y. So 15 is the data for the second student, the 20 will be data for the second student in the second quiz. So you can get the z-value of this number in this sample, you can get the z-value of this number in this sample, and then you make a product, and then this is for the student number 2, but you can make for every other students, and then you make a sum of all of that, and then you make an average, which means you divide with the how many things you have. You have 10 things, 10 students. This is the idea of Carl Pearson, how to quantify this correlation. So you have the formula that is basically calculate the z-value of every single x there, calculate the z-value of every single y, multiply the z-value of x and z-value of y that are for the same pair, and sum all of that, and then divide with how many you have. That's an average of product of z-values. That is what a Pearson correlation coefficient is. Now, what is a z-value? Z-value tells you how much you are in terms of standard deviation away from the mean. So, for example, if the average height of a 18-year-old is 70 inches, so we talked about it before, and you have a person that is 76 inches tall, since the standard deviation is 3, then we can assume that's a population standard deviation. We talk about it, right? And so somebody who is 76 inches tall is 6 inches above the average. And that is in terms of standard deviation 2. Because there are 2 standard deviations. So you get 76 inches tall person is 2 times 3, 6 inches taller than the average, which is 70. So z-value of his height is 2. So basically, z-value tells you where you are in terms of standard deviation away from the mean. If it's negative, then of course you're below the mean. If it's positive, then you're above the mean. So basically, what happens here, at least you can understand what's going to happen here. If somebody is above the average, and in the first quiz, and above the average in the second quiz, then this number is going to be bigger, right? If it's a lot above the average, this number is going to be quite a bit bigger. And now, if you have everybody like that, that would mean that anybody who scored higher on the first quiz score higher on the second quiz. Now, if you talk about the people that are below average on the first quiz, so this is going to be negative, and this is going to be negative because they're going to be below average on the second quiz, right? The worse first quiz, the worse second quiz. And again, this is going to be a positive number. And if they go away from that a lot, then it's going to be a bigger number. So everything's going to be positive here if you have that kind of relation, right? Higher the first quiz score, higher the second quiz score, or lower the first quiz score, lower the second quiz score. So you're going to have this bigger. And now you're going to divide with the how many things you have. So you're going to have an average jump away from the mean in terms of a standard deviation. So that should indicate something significant. That should come up with something significant. So if that is the case, like we see here, the bigger first quiz score, the bigger second quiz score, you're going to have this number bigger. All right? So that's an important idea. Now, You could have something different. You could have a situation that this goes down like that. So when the first quiz score is bigger than the second quiz score is smaller. Now that's not going to happen, of course, in calculus quiz, but it could happen in some other correlations data. Like, for example, I'm going to have another example, which is in the paper, that when you put more police officers on duty, you have less muggings. So that would be more police officers, less violation of the law, right? So that could also happen. In that case, this number would turn out to be negative. So that's the basic idea. But of course, this is not very attractive to calculate, because you have to calculate every single z value here. So if you work this out with algebra, and there's some story in the lecture you might want to read, you're going to end up with a little better formula to work with. And that better formula to work with is going to be the following one. So this is the same thing, only a different formula. This is our first formula that we're going to have for this correlation coefficient dr. So this and this is the same thing. Again, you need to prove that by the algebra. We're not going there. You can read the lecture if you understand the algebra there. Great, but that's the formula that we're going to have. This is the first formula. I'm going to call this 1-1 formula. Right? Label 1-1. So we're going to have two more formulas to calculate it. There are actually even more formula. So what's in this formula? You have summation of xy, which means that you actually have to make another part here. You're going to have to multiply x and y. So if you multiply 17 and 15, you're going to have 255. If you multiply 15 and 20, you're going to have 300. You multiply these two, you're going to have 0. You multiply these two, you're going to have 150. So that's a product of x and y. You multiply 15 and 15, you get 225. You multiply 8 and 10, you get 80. You multiply 20 and 20, you get 400. You multiply 15 and 17, I don't know that, but according to what I have here written in the table, it's 255. You multiply 8 and 10, you get 80, and you multiply the last, you get 50. And you make a sum again on the bottom, and that's 1795. Okay, so this is the number that goes here, 1795. And down there you have the number of the pairs, which is 10. Okay, and the means are, I already calculated the means, so this is the 11.5 for the mean of the x's. I'm going to erase this label. And I have the mean of the y's, so I have to make that here. And downstairs, I need to calculate 2 population standard deviation. Okay, I know this is not attractive, but you can do it with your calculator. You've done that in 1 or 3. Population standard deviation. So you have a sample, but you're calculating population standard deviation of this sample. So you're treating it like you have a population. Right? That is needed for the theoretical z values. You can't use a sample standard deviation for calculating z values. You need to use a population standard deviation. So one way or the other, you can come up with those numbers, and I come up with like 5.75 for the first one, approximately. So now I'm already doing approximation here, right? I'm not going to have exact value. And for the second one, the population standard deviation of the second group of this device, I come up with a 5.18 approximately. And finally, you can come up with this number. And again, this is going to be dr, the Pearson correlation coefficient. And I got 0.89 approximately. Okay. Right. So now, this is what we call a Pearson correlation coefficient. or full name, Pearson product moment linear correlation coefficient. I'll tell you what that means. Of course, the name Pearson is associated with Carl Pearson because he came up with an idea. You can read about him in Wikipedia. His work, the most significant work he did somewhere about 1905, at the same time when Einstein was doing his special theory of relativity. And actually they knew each other, so they had some correspondence between them. As Einstein was so much important about physics, in physics, the Pearson is that much important in statistics. So they knew each other and they correspond. So now we have the first idea how to calculate this, how to express this, what we see as a trend, how to get a number that can tell us about it, right? And this is the so-called correlation coefficient. Now, again, this is not an attractive calculation. So we have a better way of doing that. So if you work this out, so this is the first formula. The first thing that you want to do is you want to replace the population standard deviation with sample standard deviation, because this is what we usually calculate. So when you calculate data from the sample and you calculate statistics of that data, you usually calculate sample standard deviation. You don't calculate population standard deviation. So instead of having these two numbers, which are again something we usually don't calculate, we might want to use S of X and S of Y rather than the population standard deviation, right? What's the difference? The formula is the different thing, but this is actually a sample. So when you calculate population and standard deviation, you're basically treating this as a population. So it's kind of like something we usually don't do. If you have a sample, you calculate the sample statistics rather than a population statistics, right? But you can do both. So if this is done, then you come up, and I have this again in the lecture. You can read what is there. You come up with this particular formula. So this is another way of calculating that, and that is so not very attractive one. So reciprocal of the degrees of freedom, and then you have to multiply that with the sum of all x, y's, and minus, there is a difference in the formula, and you're gonna have these two. So what do we have here? We have the mean of the x's and the mean of the y. I should write that in the alphabetic order, right? So this is like a sample data. Those are those two guys. This is the same calculation whether you do population mean or sample mean. You will always just simply add the numbers and divide it how many you have. So I'm just labeling them differently. But these two guys over there that you already calculated. So 11.5 for the first sample and 13.3 for the second sample. Now n, of course, is then 10 in this particular case because you have 10 pairs. And the sum of x, y is what we have here, 1795. So you already have everything you need for this formula. You also have to divide that, but now you're dividing that rather than with the product of these two guys, you're going to have to divide that with the product of these two guys, which is the sample standard deviation. So this is the more natural formula. Why am I saying that? I mean, none of them is natural, right? Both of them are, a serious algebraic arithmetic calculation. But this formula, again, uses the population standard deviation. This formula uses the sample standard deviation. And you have, again, everything you need, it's in that table over there. So you have the n-1, which is 9. You have 10 pairs. Sum of x, y's, which is 1795. You have n, which is 10. You have the mean of x's, which is 11.5. You have the mean of y, which is 13.3. And downstairs you have a 2 sample standard deviation. So and again, if you plug that in here, you will get again exactly the same thing. You're going to get 0.89, just like we get by using this formula. So this is what we're going to call is a formula 1.2. So this we would label a 1.1 formula. This we would label as 1.2 formula. Okay. And again, this is not very attractive formula to work with. Now, why it's not very attractive? Because you have the lots of calculation. You have to calculate the sample standard deviation of x's, sample standard deviation of y. You have to get the product of x, y's. You have to have the mean of x's, the mean of y, and then all of that turned up, and you're going to come up with that number. So we have another formula. And again, I'm not going to show you how do I get this formula. You can read in the lecture, it's written there. But the formula that we finally had, and it's the practical formula, I'm going to write that one down. The practical formula that we are actually going to use most of the time is the following one. This is really a nasty looking formula. So nobody can remember that, neither can I, nor will you able to remember that, but it's actually the simplest one to use. Is this one. Okay. All right. Not an attractive formula to look at, but it's a very simple one to use. I'm going to show you that in a moment. So we will label this as 1.3 formula. Okay, they're all the same. They're all calculating the same thing. You can do some algebra here, and a serious algebra. So I'm not going to get into that. And you can show that they're all the same. They will, whatever the one calculates, the another one will give you exactly the same thing. There might be slight difference while you're calculating, because of course you're going to be rounding certain things. When you take a radical, you're probably going to round to a certain number of decimals, so it might get a little bit different from one formula to another, but that's your calculation. As far as formulas are concerned, they're calculating exactly the same thing. Now, what you have in this formula is sum of all of x, y's, which you already have here. You have sum of x's, sum of y's, which you already have here, 115, 133. And down there, you need to have a sum of x squares. So basically, what we are looking for here is to get the x squares. Now, that's not really that hard to do. So you get the x squares. 17 squared, 15 squared, 0 squared, 10 squared, 15 squared, da da da, and on you go. I know this is not the most attractive thing to do, but you can do it. I can do it, most of that by heart, because 10 squared is 100, right? 20 squared is 400. 15 squared is 225. 8 squared is 64. And 5 squared is 25. And then you need also, you're going to have to make the sum as well. So the sum of all those guys, you're going to have to work it out. You're going to have to use a calculator, I believe. And you get it by hand, of course. But I get the sum of them is 1653. Why is this moving? All right. So, and now you have to do the same thing for y squares, because the formula requires the y squares, sum of y squares here. Now, this is a square of sum of x's. Okay, this is just basically square of 115. So you have the sum of x's, and you make a square of that. You won't even need this. Okay, you won't even need the means. Only thing you need is this table. And so every time you calculate the correlation coefficient, you're simply going to make x's, y's, xy, x squares, y squares. So the y squared square of 15, 225. 20 square of that is 400. 3 square of that is 9. 15 square of that is 225. 15, another 15 square, that's 225. 8 square is 64. 20 square is 400. 17 square is 289. 10 square is 100. 10 square is 100. And you make a sum again. And that's going to be 2037. Okay? So I'm saying, well, this is the nastiest looking formula of all three. So this looks the simplest. This one doesn't look all that much. I mean, I don't know, these two are kind of the same. But this one is the nastiest looking one. You have two radicals here. You have some squaring to do, lots of differences. You have to subtract certain things. You have products, whatnot. It looks pretty bad and looks like you're going to have to do a lot of work here. However, this is more practical formula because all you need is this table. You don't need to calculate the standard deviations of the population nor of the sample. You don't need to calculate the means either. All you need to do is to get the sum of the x's, sum of the y's, sum of the xy, sum of the x squared, sum of the y squared. This is something you were doing in the, I believe, when you were calculating standard deviations as well. And then just plug it in, right? So in this particular case, what do you got? You're going to be plugging in. So I'm using this formula 1.3. N, which is 10, time, sum of xy's. Sum of xy is 1795. Okay? Then it says, subtract. There's a minus here. Sum of x's times sum of y's, which is 115 times 133. Okay? That's the numerator. Now the denominator. In the denominator, you have two radicals. The first radical and the second radical. And you have to make a product of both, right? This radical and this radical. So in the first radical, it says n, which is 10, and you have to multiply that with a sum of x squares, which is 1653. And then you have to subtract the square of the sum of the x's. Sum of the x's is 115. That's the first radical. The second radical is the same story, only for y. So you have 10 y's times the sum of the y squares. The y squares here is 2037. Okay, I don't really need a parenthesis here to multiply anyway. Minus the sum of the x's squared, y's. Sum of the y's squared. Okay, so this is a straightforward plugging in. You have this table done. You have a straightforward plugging in into the formula. So this is the most practical formula because once you have this table, all you have to do is to plug in those values in the table. And again, you will get 0.89. I know you have to work it out with your calculator, of course. So you're going to have to be very careful because you have, this is just going to be adding 0 here. This is going to have to be multiplied correctly, right? Down there you have to get this radical properly and another radical properly, and you have to make a product. So you have to do it separately if you don't have a good calculator. But eventually you're going to get 0.89. Okay. There's, of course, one more way to calculate the correlation coefficient. And you will find that if you look at the internet and various websites that are using that, it's also a practical calculation. And I put it in the appendix of this lecture. I don't want to bother you with another formula. So it'll be 1.4 formula, right? So again, we have three formulas. The first one we will never going to use, but that's the whole idea of the Pearson correlation coefficient. You can, so that's the idea that comes out of this original idea of Karl Pearson, how to quantify the correlation. And then we have a second one. We might use the second one because it's a slightly simpler one to write down, although again, you have to calculate the separately standard deviations here, which is a plenty of a calculation. You probably remember that from 1.3. I mean, 103, right? Statistics 1, I want to say. So, and then we have the third formula, this one here, which is the most practical one. For that one, you just need a table. So you need a table with x's, you need a table with y's, you need a table with x, y's, you need a table with x squares and y squares. So you have 5 column tables. And then you need to sum all of that on the bottom. And once you have all of the sums, plug it in here, and everything just clears out with a good calculator, and you will calculate the correlation coefficient. Okay? So in my second example, the example number 2 in the lecture, I'm going to ask you to read that. I have actually used, instead of the quiz score number 1, I have used the shoe size of a student. Shoe size. Okay? Now, guess what? It did not matter. In other words, there was no relation between the shoe size of a student and the second quiz score. So when you do that, if you discover any correlation between the shoe size and the quiz score in calculus, that would be something you can go on CNN, right? You can say, oh, I can see that if you have a bigger shoes, you have better calculus scores, or vice versa. I don't know. Right? But that, of course, is not true. So the knowledge of mathematics is not related to the shoe size. But you can do this calculation. And sometimes you don't know certain things, and you discover that once you do the science. So these are the shoe sizes: 10.5, 10, 11. So student has a shoe size 11, scores 3 on the second quiz. Student have a shoe size 7, scores 15 on the second quiz. I guess we are just measuring in inches because we want to put the male and female together, right? Because ordinarily the shoe sizes are differently measured. They're measured differently, but if you measure just inches, then you can put it together. 8.5, that will be a female shoe size. 8.5, 12. Another male shoe size, and then you have a 9 and 8. Okay, so again, you can do this. You can do the scatter diagram. The scatter diagram, you will see that in the lecture. I check it out there. You will see that the points are all over the place. There's no any trend that you can't see the trend because there is no correlation between the. There is no relation between the shoe size and the quiz score. So that is something you probably already expect. Again, sometimes there is a correlation that is not known to you. For example, the correlation between the smoking tobacco, how much cigarettes you smoke, for example, you can have that, and your chance of getting lung cancer. Now, 100 years ago, we did not know that there is a correlation. Now we do, okay? Or the amount of salt you eat and the blood pressure you have, okay? 30, 40 years ago, we didn't know that there is a relation. Now we do, okay? So there are certain things we discover as we go. So this is one of the way of discovering that, right? So again, according to my data, there is no correlation. You can take a look at that diagram. The diagram doesn't have any trend. The points are all over the place. You can make a graph out of that. So you have an XY, XY, XY. And so you'll see the points are not making any trend. And oh, by the way, I can show you my graph. You can see that. That's the graph of the shoe size. Scatter diagram. You can see the points are all over the place. They are not in any particular trend, right? That indicates that there is no correlation here? Which is something you can also calculate. And if you do calculate that this correlation coefficient, I'm not going to make a whole table that you're going to get something really close to 0. Okay. So now I have to say something about it. What is the meaning of this number, the R? So I calculate using the whole table, and I use this formula here. And in this story here, so this would be 94.5, and you can do the yourself, x squares and y squares. So I got the 1257.5. Then I got 914. So the xy's, the x squares, 914, and I got again 2037. That didn't change for the sum of y squares. And you can plug in this formula here, and I ended up with the approximate value of 0.0872. All right. So now the story about what is this guy telling you? I already know that I don't have a relation between x and y. If I am examining the shoe size of a student and the quiz score on the quiz number 2, I will not find the relation. And this guy is telling me some number, right? Pearson correlation coefficient says it's 0.0872. Okay. This is the story. So I'm gonna erase this formula. Okay, a little more space. Okay. If there is a correlation, so you might have something like this. The R is going to be close to 1. Or should we say closer to 1? Now, if the correlation is there, but is what we call in negative sense, it's a negative correlation. So that could be something like this. So which means the bigger X you have, the smaller Y you get. Then the R is going to be close to -1. And when there is no correlation, so if your graph gets like this, then the R is going to be close to 0. So that's the main point of the whole calculation, to see what the R is. Now this R is close to 0. You can see this is 800. That's not even a tenth. Okay, so the idea is that this is indication of no correlation, right? Well, this kind of correlation will be called positive correlation. This kind of correlation will be called negative correlation. So the closer you get to 1, the more correlation you have. And the correlation is going to be positive, which means that the bigger X, the bigger Y. If the, so this is what we know, a product of Z values on average, right? If the Z value of X goes one way and the Z value of Y goes another way, that means that when the X gets bigger, the Y gets smaller, and vice versa. When Y gets bigger, X gets smaller. Then we have a negative correlation, so which means that the R is going to be somewhere closer to -1. The closer to -1 it is, the more correlation you have, but it's a negative one, which means the the trend will be like that. And finally, when you have graph scatter like that, when you don't have any trend, then you're going to have an R close to 0. So this is an indication of that. Even without you graphing anything, you will conclude that correlation is not, there is no relation between X and Y. There is no trend on that graph. If you graph that, you'll convince yourself that that's exactly what the case is. Okay? So I have another example in the lecture, so I want you to read that. Which is about 10 days of summer, and I think it might have been 10 weeks of summer, I don't know, but it's 10 terms when in Boston Park area, it's a large area of the central Boston, we're experimenting with some 20 years ago, we're experimenting with a number of police officers on duty. And so when they tried to figure out what is the impact on the crime in the area. So they had and like the first week they have 10 police officers on duties on average, and then they get the 5 reported muggings. The second week they had 15 police officers on duty and 2 reported muggings. The third week they had 16 police officers on duty and 1 reported mugging, and on you go. Well, one way or the other, you could clearly see that when they put more police officers on duty, they get less muggings. Not a surprise. And when they have a less police officer on duty, they get more muggings. Okay? So I guess the police officers on duty were uniform, right? So when you see an uniform police officer, and you probably, if you're a criminal, you're probably not going to get involved in any kind of crime because you might get caught, right? So that's why we have that, which means in that particular sample that I have there, so I want you to read that. I'm not going to write it on the board here. I calculate the R in that particular sample, and I come up with the negative R, as in negative correlation. So let me write the data down, just the data without the whole calculation. But the whole calculation is in the lecture. And of course, I want you to read the lecture. So we have the police officers on duty and the number of reported muggings. So in this particular example, so 10 police officers on duty, reported muggings was 5. 15 police officers, 2 muggings. 16 police officers, 1 mugging. 1 police officers and 9 muggings. 4 police officers, 7 muggings. 6 police officers, 8 muggings. 18 police officers on duty, 1 mugging. So somebody was mugging even with lots of police around. Well, okay. 12 police officers on duty, 5 muggings. 14 police officers on duty, 3 muggings. And 7 police officers on duty, 6 muggings. Okay. And then you have the sum down there would be 103. So they have on average 10.3 police officers on duty. You divide this with 10.3 police officers on duty on average. And they had on average 4.7 muggings. So the total number of muggings is 47 in that summer. Okay. So if you calculate, again, you would use that formula that we have, we labeled it the 1.3 formula. If you calculate that, you got the R to be in this calculation 0.969. This is very close to 1, right? 0.97, basically, if you use 2 decimals. This is very close to 1. It's 300ths away from 1. Of course, it's negative. Negative means that the trend is like that. Okay, the trend is down. So again, I can show you my graph. This is a graph from the lecture. This is again Boston Park example. So this is how the graph looks like, right? So when you increase the number of police officers on duty, when you increase the X, the Y goes down. the y gets smaller, and you have this trend. You can clearly see this trend going down. The points are going from the top right, from the top left corner to the bottom right corner. So that's when you get the negative correlation, and we call it negative correlation. Then you have the R going to be a negative number. The Pearson correlation coefficient will be a negative number. Okay? Not a surprise. Again, the more police officers you put on duty, the less muggings you're going to have. So that is a common sense. Okay? So that calculation is there. So there are a couple of things you need to know about R, right? R will always be a number between 1 and -1. Now that's a calculus fact. As a matter of fact, this is something you can prove with just using algebra. I am not going there. But R, the way it was conceived, that initial formula we have from Carl Pearson, the way that formula is done, it will never be a number bigger than 1, and it will never be a number smaller than -1. It could be anything in between. -1 and 1. Anything in this range, okay? So you gotta remember that. If it goes closer to 1, that means the trend is like that you will have trend that will indicate the bigger X, the bigger Y. It doesn't have to be steep. It could be just a small increase like that. It could be a large increase. But the thing is going to happen that you're going to have something that is going from a bottom left to the top right. Something like this. Okay? When it gets closer to -1, you're going to have a trend that looks like this. Right? Like the Boston Park mugging problem. And when it gets around 0, then you're going to have a trend that is not indicating any linear connection. So that's an important thing. Without any calculation, when you see something like this, as R is -0.969, I already know that this is how the trend is going to look like. So that's the first thing to remember. So R is anything between -1 and 1. If it's close to 1, we call it the positive correlation. If it's close to -1, we call it the negative correlation. If it's close around 0, then we will say no correlation. But there's another trick about it. The way that this correlation coefficient was conceived, it will reveal only linear correlation. What do I mean by that? For example, you can have a correlation like this. And you would say, hey, I see something here. I see a parabola. This is a shape here that we call in geometry parabola. So there is a correlation. There is a relation. Up to this point, I'm moving down. After this point, I'm moving up. And I'm moving that, if you tell me what an X is, if this is your X, I can tell you what a Y is going to be. So there is a relation between an X and Y. But the relation is not in terms of line. It's in terms of parabola. So guess what's going to happen? The R is going to be 0. So which means that the Pearson correlation coefficient will not discover the trend that is not linear. It will only discover the trends that are linear. So the R will tell you about a linear trend. Linear trend is lines, right? That's a linear trend. The trends that are non-linear, so this is one kind of trend that is not linear, you can as well get a circle. Like, you know, here you have a trend. You're not going to have any data like that, but you could. The R will tell you 0, meaning that R is linear correlation coefficient. And you have to remember that always. It can only discover linear trends. It is not made to discover the trends that are parabolic or exponential. Okay? Now, if you want to discover those trends, you're going to have to do something else about it. Some of them can be reduced with the proper function. They can be scaled to linear trends. Some of them, they cannot be done that way. So we have other kinds of correlation coefficients that we can calculate for other kinds of trends. But you got to remember the Pearson correlation coefficient only refers to linear trends. Okay? So if the trend is non-linear, but there is a trend, the Pearson correlation coefficient will tell you 0. There is no trend. The trend might be there. Again, so you got to be aware of that. So this is the second thing you got to remember about it. So that's why we call it Pearson product moment linear correlation coefficient. Linear as in line. Linea is Latin for a line. Right? This is Latin word that is meaning line. When we drop the A at the end, we get exactly the Anglo-Saxon English word line. Right, those kind of trends. One more thing to remember, and this is also very important. Correlation does not mean causation. Okay, you're gonna have to remember that. Even scientists very often make mistake by thinking that this is the same thing. It isn't. Okay. When X and Y are related, that does not mean that Y is the way it is because of X. No. Or that X is the way it is because of Y. No. They are just related. Okay? What do I mean by that? Take a look at this quiz example. We have a quiz number 1 and quiz number 2. And they are probably in calculus on different topics. So the score on the quiz number 1 has nothing to do with the quiz number 2 because they're different topics. They might be slightly related, but probably not. Okay? So that you could study for the quiz number 1 and get really good score there, but if you don't study for the quiz number 2, that score will mean nothing. You will get lousy grade on the quiz number 2 because you didn't study for that one. Meaning that whatever you get as quiz number 1 doesn't have an impact on quiz number 2. There is something else important there. It's important whether the student is, the reason why they are related, it's not because one implies the other, but because the one who study for the quiz number 2 is more likely to study, the one who study for quiz number 1 is more likely to study for the quiz number 2. It's better student. Maybe smarter too. Smarter on quiz number 1 is smarter on the quiz number 2. The IQ will not change, right? Maybe he has better condition to study, more time to study, and all other things that can go with that. But there are other factors, and the quiz score number 1 is not the one that implies the quiz score number 2. But there are some other factors that are relating them, okay? That's very important to know. So sometimes you can discover a correlation which is not causal, which means that X will not cause Y, nor Y will cause X. They're just related because of some other factors. And you have to be aware of that. Sometimes there is a causation. If you think about this Boston Park example, that you have exactly causation. Because if I put a number of police officers on duty, this is a large number of police officers on duty, that will cause the number of muggings to go down. Because the criminals are not entirely stupid. So when they see lots of police officers, they're not going to be doing muggings, right? So this time you can see there is a causation, but I'm not saying there is a causation because I calculated it. No, I'm using a common sense. Now, so you might say, oh, maybe that is not so. Okay, I am just saying that I believe there is a causation. There is also a correlation with this number, right? Negative correlation, very close to -1. But I'm claiming causation because I believe there is a causation there, which means that the number of mugging is directly related to the number of police officers on duty. The number of police officers on duty causes this other number to go up or down. Okay? So there, I think there is a causation, but this is not scientific conclusion. I'm not making that conclusion based on some calculation. No, I'm just using common sense. And in science, common sense should be avoided. You could use that to prompt yourself for some research, but research should not be based on a common sense. It should be based on calculation, right? So what this guy can discover to you is linear correlation, trend in terms of a line. It will not discover the trends that are not linear. That's number one thing for you to remember. Number two things for you to remember is that it does not mean causation. It only means correlation. So when you see this for police officer duty, that only means that X and Y, the police officer on duty and the number of muggings is related. Whether they are related in a causal way, which means that the first one causes the second one, or the second one causes the first one. Now, in this particular case, of course, the number of police officers causes the number of muggings to go up or down. So the first one causes the second one. That is my common sense. Again, I'm using the common sense, and the common sense tells me that we have a causation. But in general, correlation is not the same as causation. Okay? To calculate causation, you're going to have to do something else. Yes, it is possible to get that done, but not with the R. Right? So you got to remember that. Sometimes, very often, people mistake one for the other. So I'm going to give you an example. I'm going back to this salt thing and the blood pressure. We know that if you eat more salt, you're going to have higher blood pressure. And if you eat less salt, you're going to have less blood pressure. Okay? Is that a causal effect? Would that mean that you should avoid to eat salt because it causes you to have a higher blood pressure? Well, some people say yes, some people say no. Some people say, well, that's just a condition. When the people have the higher blood pressure, they tend to have a yearning to eat salty food. Well, I really don't know. I'm not a medical expert, so I don't know. We do know that there's a correlation. Whether that's direct causation, so that intake of salt really causes the blood pressure to go up or down, that I don't know. It might well be. But if you want to say that's the case, you have to prove that. You have to show a convincing data for that. So which means you have to eliminate all of the other factors that might be involved. Right? So that can be done. But R by itself will not tell you that. Also, there's another thing about R, which we're going to be talking the next time around. If the sample is very small,
So for example, here is my small sample. All right? 2 pieces of data in the sample only. Now I have like 2 students or 2 days of summer for 2 police officers, one day of summer for 1 police, I don't know, 1 number of police officers, another day of summer for another police officer. And muggings, whatever that will mean. You have a linear trend. You will always have a linear trend if the sample is like small like that. You have 2 points, you will have a linear trend, of course. Does that mean that you have a significant correlation? No. You cannot make conclusion out of 2 pieces of data. So 2 pairs. So you have like, you have an X and you have a Y, and this one is like, what would that be? Like 2, 2. And the other one would be like, I don't know, 5, 4. And no matter how you take it, it will be a line through it. But this kind of sample cannot be used. This pair data, so you have the X2 and 5 and Y2 and 4, you cannot use that to conclude that you have a correlation. However, when you use R, you can calculate, and R will come up to be perfect 1. Because it says, hey, I can put a line through it. And if you can put a line through it, you have a linear trend. The R will come up as 1. However, you cannot conclude that because your sample is too small, right? So basically, what we're talking here is that there is another thing in the game here is the size of the sample. So the next time we meet, which is on Wednesday, we're going to be talking about how is the correlation significant? What does it mean that correlation is significant? Would you just say when R is 1 or -1? When R is 1, positive significant correlation. When R is -1, negative significant correlation? Or do we need to consider the size of the sample? So I already gave you the answer to that. Yeah, we need to consider the size of the sample. R by itself, 1 or -1, is not enough. That's an example right here. You can do the calculation yourself. You can use the formula 1, 2, 1, 3, or 1, 4, or 1, 1, 1 if you really like, and you will always get the R being 1. It's very easy to get the X squares, the Y squares, the XYs, and you can plug it in that third formula, and you will calculate the R will be 1. But you cannot conclude that there is a significant correlation here because the sample is going to be too small. So besides knowing what R is, you also need to consider the size of the sample. That is a story about the testing of significance of correlation. So let me give you another example. In the story about mathematics and the success in mathematics and IQ, we know that R, you look at the IQ scores and you look at the success in mathematics, and R usually comes up as 0.7. It's not perfect 1. 0.7, it's not 1. But we do know that the higher IQ scores and higher math scores are related very strongly. There is a significant correlation. Okay? It's not a perfect correlation. It's not 1, but there is a significant correlation. Why do we know that? Because we have done this on many students. They have taken IQ tests, and then we look at their success in mathematics. So we know there is a significant correlation, even though the R is not 1. So there are some other things in the game besides an IQ, but we know that correlation is significant. Again, because we have done that on many students, so we have a huge sample to refer to. Right? So again, when you have an R calculated, that's just one piece of the information you have. You still need to investigate whether the correlation that you have, if R is close to -1 or close to 1, there might be a significant correlation. But to conclude that, you need to consider the size of the sample and you need to do some hypothesis testing about it. So we'll talk about it on Wednesday, all right? So I'm gonna end this story today. And this concludes our topic for the test number 2. On the test number 2, you will have one sample in which you have to calculate the R. So I strongly advise you to go to the homework and do there are pieces of that homework that you can calculate different things. You will be asked different things, but you calculate the R only. Make sure you know how to calculate the R, because you're gonna get a question on the test to calculate the R. And that's the test number 2 I'm talking about. It's next Monday. But we're going to be talking more about correlation next time with me. We will talk about it. How do you actually discover that correlation is statistically significant, rather than having a situation like that. Oh, I have a correlation, perfect correlation, but I don't really have any significance here because my sample is way too small to make those kind of conclusions, right? Okay, I'm going to end the stream. Hopefully you understand this. And again, you need to read the lecture. The lecture has a little more calculation, a little more example is written in a way that you could check out all the calculations, all the numbers. And the appendix of that lecture appendix contains another formula for calculating the Pearson correlation coefficient, and that formula is not something we will use, but you can find it on the internet. So if you find it on the internet, don't get surprised. That's just another way of calculating R. All right? I'll see you on Wednesday.